So today we'll continue the discussion about input language of Klingo, and we'll probably finish most of the sections in chapter 2. And chapter 3 is about using this construct that you learned in chapter 2. How do you do the actual programming? So currently we are still doing some small programming exercises, but when you build up these ideas, it'll give you some interesting programming. So we did this before, but let's just recall what we did. So for the choice rules, many of the answers of programming start from writing the choice rules. And basic idea is a choice. So you can choose from this set, P of A, comma, Q of B. Okay, we write semicolon to distinguish the, have a semicolon as a separator, but it basically is a set that contains two elements. And choice rule here is to say that you choose any subset of this total set. And how many subsets are there? P of A, Q of B, how many subsets are there? 4, right? So this is something that you can easily say that these are the 4, right? So the first one is you don't choose none of them, right? The second one, you choose P of A but do not choose Q of B. And the third one is you choose Q of B but do not choose P of A. Fourth one is choose both of them. These are the all possible choices. And when you see this, you should know by now that there are 2 choices for this, 2 choices for this, and 2 times 2 is 4. There are 4 choices possible. Okay? And we also look at this pooling and interval to write choice rules more succinctly. If you have pooling, then the first one that you see as a pooling is you can use the semicolon separated list, or you can use interval if this happens to be numbers. You can use intervals to denote this. Okay? And you can also write the cardinality bounds in this choice rule. So 1 and 2, this gives the bounds of this set. So when you do this one, you're choosing the subset of P1, P2, P3, but it should contain at least 1 element and at most 2 elements. Okay? So that gives us 6 choices possible, because empty set does not satisfy the cardinality bound, as well as total set does not contain the satisfies the cardinality bound. Now, with that, we can actually do a bit more interesting programming here using the concept of choice, local and global variables. So in Klingo, you can write this rule P of I colon I equals 1.7. Okay, so Klingo rules are very intuitive. So what do you expect? Let me actually go over this one first. When you write this rule, okay, the Klingo understand this in terms of the expansion. So I goes from 1 to 7, meaning that you have actually 7 atoms in this choice. You can choose P of 1, P of 2, P of 3, up to P of 7. That's what this rule is about. And this is the first time that you see so-called local variable. So the definition of local variable goes like this. It's a variable I, right? So you remember the capital letters stand for the variables. The local variables are the ones that have all these occurrences confined within the set braces. Okay? So here, if you see, so here we have I as the only variable in this rule, and this I occurs only inside the set braces. Then it is called local. Okay? When you see a variable, actually I'm going to show another example that has local global variables in the next slide. But local variable is only within these set braces, and what they do is to expand the set inside. Okay? So this is something that you already are used to when you say this condition in the set notation. This is like what is I that we range over. So I is from 1 to 7, so you can expect that way, right? Questions? Nathan, that you? Questions? No? All right, so a local variable and then global variable. So let's actually look at the answer to this question. So actually, let me open the Socrative and try to answer these questions. You already know what is choice rules. So okay, so how many stable models are there? Okay, so let's open now. So the majority chose E, 128, because it's 2 to the power of 7. I don't understand why people chose C and D, okay? So if you chose C and D, think again. This is choice, and I just told you each of the atoms have 2 choices. So if you have 7 atoms, it is 2 times 2 times 2 times 2 times 2 times 2 times 2. I don't know how many times I say 2, but there should be 7 2s. So 2 to the power of 7 there, okay? So the answer is E. All right, now let's look at the other one. So here, is I a local variable or global variable? It's global, right? Why? Because this time, there is an occurrence of I outside the set brace. So there are 2 occurrences of I, but one of the occurrence is outside the set brace. It's called global variable. And what global variable does is it generates many, many rules. Okay? So this time, instead of making the rule larger in horizon, is actually making more rules in the vertically. Right? So you have I equals 1 to 7. So when I equals 1, you get P of 1 choice. I equals 2, P of 2 choice, and so on and so forth. So just contrast this with this one. So here when I was used as a local variable, okay, all the occurrences of I was inside set brace. In this case, this rule extends to this. There's still only one rule, but this rule, the one rule has now 7 atoms. On the other hand, in this case, I is a global variables, and each rule has only 1 atom, but there are 7 rules there. Okay? All right, so let's do this again. How many stable models are there? Actually, I should not show you this thing. How many stable models are there? Okay, so let's see. Okay, so maybe let me just go over here. The answer is actually 128. Okay, if you chose again 7, I don't understand why, but here the idea is the same. For each of the rules that it gives 2 choices. So P of 1, you have 2 choices to include P of 1 or not. Same for P of 2 and so on and so forth. So you may wonder then why do we bother with this? Because for this particular example, it works in the same way. Okay, so here is actually an interesting one that you will see often in the actual programming. So what is the local variable and global variable in this example? So is I local or global? Global. What about the J? J is local. Good. So you understand what it is going on. I is global because there's an occurrence of I outside the set brace. But if you look at J, all the occurrences of J is inside set braces. So what happens here is the I makes the rule expanded. So actually, let me just write step by step. Okay. So when you see this global variable, it will first generate multiple rules. Remember, the global variable generate multiple rules based on the instances. So if I equals 1, this will give 1 comma j. Don't touch the local variable yet. So you have this one. Okay. When I equals 2, okay, remember I goes from 1 to 2. So when I equals 2, this I is also 2. So 2 comma j, j equals 1 dot dot 3. Okay, so this is the first step that you get. And after that, you have only local variables, so you can expand the local variables. So the first one here, expand into q1 comma 1. Remember, j goes from 1 to 3. So we have 1 comma 2, 1 comma 3. Okay, the second rule is doing same, but here 2 comma 1, 2 comma 2, 2 comma 3. So this is what you get. Okay, remember when you have both local variable and global variable, try to ground global variable first and then do the local variables. Then you will get the ground instances. Okay? So then the question is, how many stable models are there? So let's actually do this again. So for this program, okay, when I give you this, mentally you have to convert into the ground rules that you see here, and then try to find out how many stable models are there. Okay? So how many stable models are there now? Okay. So the majority answer is D. Okay, and majority is right here. Why? Because if you look at the first rule, there are 3 atoms, so there are 8 choices, 2 to the power of 3 for the first. Okay, and for the second one, again, you have 8 choices. So 8 times 8 gives you 64. Okay. If you want to see every 64 stable model, then you're welcome to type in the Klingo and find it out. Okay. Of course, now you understand the choice rule can contain variables. So here x, is it local or global? Global. So when you see this, the Klingo will first try to turn this into okay. Okay. So it'll first turn x in, replace x with 1 and generate one ground rule. And the second, x equals 2, generated. How many stable models are here? 4. Because the first rule, you have to choose exactly one from P of 1 and Q of 1. So you can have two choices. Either choose P of 1 or Q of 1. Remember that there is a cardinality bounds. You have to choose exactly one from the first set. And you also have to choose exactly one from the second set. And that gives you 4 choices, as you see from these answers. Okay. So x here is a global variable. And yeah, so that's what he said. Now, you often see that there is a lower bound and upper bound to be the same. In this case, Klingo has alternative syntax. You can just use equal 1. Okay? So when you see equal 1 in the with the set, that means the lower bound and upper bound are both 1. Okay? So we are going to use this interchangeably. Okay, now it's your turn. I ask you how many stable models are here, but maybe it's better to answer what are the stable models, but how many stable models are here? That's actually better to answer. Let me give you choices. Okay, so let me finish and open the quiz. So the question is, how many stable models are there for this program? And you're welcome to talk to your neighbor if you want. So again, mentally ground the global variable. So replace the global variable with instances, and then try to look into the rule, what that rule means, and find out how many stable models will be there. Okay, so So this is the end result. So D is the majority. It's actually not very clear. I mean, there are also many people also chose E as the answer. Okay, so let's see what is going on. As I told you, first try to ground the global variables. Okay, so here x goes from 1 to 3. How many rules do we get when you ground it? When you replace the x with the instances, how many rules do we get? 3, right? So when x equals 1, oops, this gives 1 dot dot 1 dot 2 equals 1. P 2 1 dot dot 2. So it's basically the same as algebra. You are substituting the instance for variables, but don't change the other part. You just leave as it is. Okay? So this gives better idea. Okay? So the first rule is saying that you have P of 1. In fact, this is actually using the interval. How many atoms are in this first rule that I wrote here? So let me tell you, actually, this rule can be further expanded into the base form because here we are using the interval to shorten. What it means is actually P of 1, 1 and P of 1, 2. And P of 2, 1, P of 2, 2, P of 3, 1, P of 3, 2. Okay, so then it gives you a better idea. So the first rule is saying that you have to choose 1 from this. And note here that this is equal 1, so you have to choose exactly 1 from this set. There are 2 choices. You can choose this one or you can choose this one. Okay, so only 2 choices here. Here again, you have 2 choices. Again, you have 2 choices. 2 times 2 times 2 is 8. So the answer is 8. Okay? Any question up to this part? All right. So if you're more used to, then I would encourage you to try to guess the stable model from this one directly. Okay, so of course this is actually good to do if you want to know the details, but when you do the programming, you don't have enough time to do these things always, right? I mean, if you're used to, you can just look into this. So here, x goes from 1 to 3, and each of the possible values of x, you have to choose 1 or 2, okay? Exactly one of them. So there are 8 choices possible. If you're more advanced in reading these rules, you may be able to find the stable model from this one directly. But if you're not, okay, you're still learning for the first time, try to ground it and starting from here, okay? So you need some experience to write these rules more compactly. All right. Sometimes you want to use this one not only for the intervals or numbers, but you want to use it for the other predicate. So for instance, actually, let me start with this one first. This is already what we said. This is elected predicate that has 1, 2, 3, 4, 5, 6 members. Okay, so you have to select 3 members out of these 6 people. So 6 choose 3. Okay, you can write Klingo to return the all possible 6 choose 3 possibilities in this way, giving the lower bound 3 and upper bound 3, or you can do the equals 3. Okay. Now, you can write this more succinctly if you know these as a database fact. So you know all the people's name. Okay, just write as a one predicate using this pooling. And then here we say X arranges over the person X. And among them, you have to choose 3. So there are 6 people here, but you choose only 3 out of them. Okay? So how many stable models will be there if you ask this program? 6 choose 3. 20. 20 should be the possible choices. Okay. All right. Here's an exercise problem, and let's actually do the first one together. So we are given this program, P of A, B, and Q goes 1 to 4. The first question is asking how can we rewrite this last rule here without using the local variables. So how can we do that? So what is local variable in the last rule? Is it X or Y? Is it X or Y? Anna, is it X or Y? You have 50-50 chance. X. So X is local because there are two occurrences of X in the set brace, and both of them are inside, right? Inside the set brace. So we want to write without using the local variable. And this is actually the idea. So note here that X ranges over A and B because P of X, there are two instances of P of X, so P of A and P of B. So what you need to do is just to replace that X with the possible instances. So what I did here is just to make this set large, okay, because X can range over A and B, right? So just write R of A comma Y and R of B comma Y, and then you don't have to use local variables, okay? And how many stable models will be there? Well, this is what you have to figure it out, okay? So I'm going to skip it because you can do this. The next topic is about the constraint. Now, constraint is a very specific form of the rules that has nothing to the left-hand side of the colon equal. So the left part of the colon equal sign is called head, but there's actually no head. Internally, this is understood as bottom implies P of 1. In the recitation section this week, I asked the TA to go over how these Klingo rules are mapped to the propositional logic, okay? And then you will see how to read this Klingo rule as a formula in propositional logic, okay? Now, so when you see this one, P of 1 implies bottom, it's actually same as P of 1 is false, right? So that's what this rule is meaning. You are asking that P of 1 should not be in the stable model. That's what this rule is saying. If you have P of 1 in the stable model, it will derive the bottom, which is a contradiction. In other words, in order not to derive this contradiction, you have to, you should not include P of 1. That's what this rule is about. Okay? So in other words, constraints are used with choice rules to weed out undesirable stable models for which the constraint is violated. The stable model that contains this P of 1 is violating the constraint. So that should be weed out. Okay, so let's actually do the exercises. So here, maybe let's just look at the first one, P of X, where X equals 1 to 2. Don't look at the second rule here. How many stable models are there? If you look at the first rule only, 4. That's what we said before, right? P of 1 and P of 2, all the possible subsets of the P of 1, P of 2 is a stable model of this. So let me actually write here. If you look at only this one, okay, so the stable models will be empty set, or P of 1, P of 2, P of 1, 2. Now, what the second rule is saying is, among these 4 stable models, if they contain P of 1, then remove that from the stable model. Okay, because when it contains P of 1, this leads to the contradiction. Okay, so now let's consider both of them together. How many stable models are there? So remember, when you add this constraint, you're only removing some stable models of the original program that violate the constraint. In other words, among these 4 stable models, each of them, if it contains P of 1, then you are going to remove it. Okay? Then the remaining one will be the still stable model. Okay, so what could be the stable model? Empty set. So, okay, empty set does not satisfy P of 1. In other words, it does not violate this thing. So empty set is a stable model. What about P of 1? P of 1 violate because P of 1 makes this true. So true implies false is false. Okay, that's not going to work. P of 2, how about this? Does it work? Yes. So that we have P of 2 as the stable model. What about this last one? P of 1, comma P of 2. Does it satisfy the constraint? Anna says no, right? P of 1, P of 2 does not satisfy the last one because it contains P of 1. This is the interpretation that makes P of 1 and P of 2 to be true. Okay? So under that interpretation, P of 1 implies bottom is false. Okay? Remember this one, P of 1 implies bottom. When this becomes true? P1 implies bottom is true when P1 is false, right? The last one is say P1 is true, so it cannot be satisfying the constraint. So the answer is only these two. Okay? So remember what the constraint is saying. You can think about this kind of negation. This rule is saying P of 1 should be false. But if you look at the last one, P of 1 is true. So it cannot satisfy the constraint. Same as the second one, P of 1 does not satisfy the constraint. The constraint is saying P of 1 should be false. And the second and fourth one does not satisfy that. Okay? So we are going to do more exercises. So if you have questions, let me know now. Catherine, question? No? Clear? Yeah. Okay. All right, so the next one is this one. Okay? So let me ask you, you can talk with your neighbor if you want. Find out all the stable models here. I'll give you 1 minute to think about, and I'll open the Socrative. So this one is actually short answer questions. So remember, the answer is actually either 0, 1, 2, 3, 4, because you cannot have more than the whole 4 stable model here. By adding the constraint, you're only going to eliminate some of these stable models, right? You're not going to introduce more stable models. So what among these 4 stable models, what will be eliminated? The question was actually write the stable model, not the number of stable models. Write the stable model this time. It's a short answer question, not the multi-choice. Okay, So okay, the answers are actually very diverse, so there's no need to look into this. So let's do this together. The last rule is saying that if the stable model satisfies both P1 and P2, this violates the constraint. So among these four stable models, which ones are violating the last constraint? Huh? Only the last one. Only the last one. Okay? So the last one contains both P1 and P2. So this rule is saying that do not contain both P1 and P2. Read it as negation. Do not contain both P1 and P2. Okay, then the first three satisfy that constraint, but the last one does not. So the answer is the first three. So they are the stable models. Okay, now this becomes more tricky for the next one. Okay. What could be the stable model? This is a bit hard. Can anyone guess what is the stable model for the last one? This one, you can understand this in terms of propositional logic, right? And I said this is kind of negation. So it's a negation of P1 and negation of P2. Okay, I need actually use more parentheses than necessary. Now using the De Morgan's law, okay, you put the negation inside, it cancels out. And basically, the last rule is saying you should choose either P of 1 or P of 2 or both. Meaning that empty set does not satisfy this constraint. So the answer set or stable model becomes P of 1, P of 2, P of 1, P of 2. Okay, so you can read it, so only the empty set does not satisfy this constraint because empty set does not have P1 and does not have P2, so it violates the constraint. All the other things do not violate the constraint. Now sometimes, because this may look a bit involved because you have to have both double negation, but you already know how to write the formula equivalently using some classical, using equivalence in propositional logic, okay? If you don't, you can still read it like, if the stable model does not contain P1 and does not contain P2, then this violates the constraint. Which one does that? Empty set. Empty set does not satisfy, does not have P1 and does not have P2, so it violates the constraint. All right, there's one other things, and I'll just leave it as an exercise, okay? You can write in Klingo and you can verify your answer, okay? I'll give as an exercise problem. If you don't know why Klingo is returning that solution, you can post on the Piazza and we can answer from there. All right. So we already look at the choice rule with cardinality bounds, and sometimes these bounds, the number can be removed, and then instead we can use the constraint. So before you have seen this P of A, Q of B, and this one has the meaning as choose a subset of PA and QB, but at most one from them, right? So how many stable models will be there for this one? You choose subsets of PA and QB, but the cardinality of subset is up to 1. Okay, upper bound is 1. How many possible subsets are there? First, let's forget about this bound. How many subsets are there? 4. Among them, how many satisfies the upper bound to be 1? 3. Okay, so let me do this again. Okay, so here empty set and P of A and Q of B and P of A and Q of B. Cardinality of the set means how many elements are in the set. So the first one, the cardinality is 0. Okay, this one's cardinality is 0, this one's cardinality is 1, this one is also 1, this one is 2. So we say up to 1 means that we don't get this one. So there are only 3 remaining. So those are the stable models. So if you have 1 here, then these are the 3 stable models whose cardinality is up to 1. And this is actually same as you choose all the subsets, but do not include the last guy. Okay, so you can rewrite this cardinality bounds equivalently using this constraint. Okay, so Klingo returns the same stable models for either of these input. And here is an exercise. I don't know whether you can do this. Let me try. Let me actually open this as a participation credit problem. Okay, so based on what we just did, okay, can you find a similar transformation now with this one? And this one has low bound to be 1, not the upper bound. Okay, how can we rewrite this one using choice rule and the constraint, but no upper bound and lower bound constraint? Let me first open this chance to anyone who didn't have participation credit yet. I'll give you 30 seconds. Want to try? Welcome to do. Come here. So the idea is you have to choose at least one, right? Meaning that you're going to eliminate some of this stable model here, right?
So I was thinking it would be like kind of like on the last slide, just not PA, not QB. Like that.
Okay, almost. Can you complete? Too much. So the last slide, yeah, you got it right. I'm referring to the last slide to answer this question. In the last slide, let me actually give you another hint. So in the last slide, we did this problem, right? Yeah. Okay. So can you actually correct some minor mistakes there? So the question now is a bit different. This one, right? Okay, that's good. You probably need also the choice rule, right?
Yeah.
Because this is only going to remove, right? So also let's add it. Any question? Doubt? Okay, so let's read together. So you're choosing any subsets of PA and QB, but you don't allow one particular case that P of A is not there, also Q of B is not there, meaning that you're going to eliminate empty set. Okay? So empty set is the only one that has lower bound less than 1, right? So if you use this rule, what we expect to be the stable model is P of A, Q of B, and P of A and Q of B, because these are the subsets of this guy, but the lower bound cardinality is at least 1, right? So this cardinality is 1, 1, this is 2. 2 is greater than 1 still, right? So these three satisfy the constraint, and same as this one. So it's a subset of this, except for empty set. The empty set does not have this and does not have this, so it violates. Okay? On the other hand, this guy, for instance, has P of A. So P of A is true, meaning that this is false. False implies anything is true. So this constraint is not violated. Same for Q of B, same for P of A and Q of B. Okay, good. Why don't you write your name? And Prashant, write down this name too. Okay, great. So we solved one problem. All right, so the next section of today's talk, probably the last section, is about how to represent functions in ASP. Now, recall that we have done this before. We talk about the definition of function, one-to-one function, on-to function, and one-to-one correspondence. The nice thing is now we can actually compute these functions using Klingo. Okay? And that gives you a very powerful programming technique, because many of the problems out there are about the functions, and you can easily encode these functions in the language of Klingo. And we'll utilize this idea in the next class when you go into more challenging combinatorial search problems. So recall, this is actually the slide that you see before. We worked out this, and when you have A equals 1, 2, 3, and B equals AB, then how many functions are there? One can choose, so each element of A, you have to choose exactly one element from B, right? So one can choose either A or B, two can choose either A or B, three can choose A or B. So there are 8 possibilities, there are 8 functions, right? That's what you studied before. And now what we are going to do is to encode this idea in the language of Klingo. Okay? So given the mathematical definition, can we turn this into the language of Klingo? That's what we are going to do. So let's recall what is the definition of a function. A function is defined between two sets, A and B, such that for every element, small x in A, there is exactly one element in y in B, such that x-y pair belongs to the function. Okay, so that's what's the definition. So how do we write the function in Klingo? We have to define what is domain and what is codomain. So this is easy. I'm referring to the example in the previous slide. Domain has 3 elements, 1, 2, 3. Codomain has 2 elements, A and B. Okay, anyone can write this one, right? What is the main idea here? This is the one-line definition of a function in the language of Klingo. So as you see here, we use local and global variables. Which one is local? Which one is global? X is global. Y is local, right? So remember, look at this. I use the global variable to range over the elements in the domain, and the local variables to range over codomain. Okay? Now when I do that, we have done similar practice before, but let's try to read it. For each element in X, this function finds exactly one element from the codomain. Do you get this idea? Okay, we did a similar thing in a different notation. But basically what it means, for each element in X, you have to choose exactly one element from the codomain. That's exactly what the definition of function is about. Okay. So this is, the last one is just a directive to show only the functions. Okay. So let me actually show you how to run. So this is the program that you saw. Okay. So how many functions are there when the domain is 1, 2, 3 and codomain is AB? 8, right? So I put 0 at the end to return all solutions. And as you see, there are 8 of them. Okay? So here, 1 is mapped to B, 2 is mapped to A, 3 is mapped to A. This is one possible function. There's another function, another function, another function. Okay? And each of these 8 represent the mapping that I showed you earlier. Okay? So here, 1 is, so if you look at the side, you see that 1 is mapped to A, 2 is mapped to A, 3 is mapped to A. That's one possible function. 1 is mapped to A, 2 is mapped to B, and 3 is mapped to B, A, B, B. That's another function. Okay? And there are actually 8 possible functions, and that's what you see in here. Okay? So let's see. Do we have a? So 1 is mapped to A, 2 is mapped to A, 3 is mapped to A. That's the function that we just saw in the previous slide. Okay? And all the way up to 1, 2, 3 are all mapped to B. Any question up to this part? All right. So you can actually compute any functions using this way. All you need to do is just changing domain and codomain. The rule here is actually the same, but you can just change the domain and codomain. And that's easy to do. Okay? You can just write any domain and codomain. All right, good. Now let's look at one-to-one function. So what is a one-to-one function? It is a function, but then every element x and y in f and x1, y in f, it is the case that x is equal to x1. What that means is if you have the case like y, and let's say x is mapped to y and x1 is also mapped to y, then these two guys should be the same people or same element, right? Okay. In other words, if they are different, then they should also map to different y's. Okay? Now, I'm going to use this definition because that's easier to write in the Klingo. Okay? So recall that if you have x mapped to y and x1 mapped to y, for this to be one-to-one, x and x1 must be the same element. That's the definition. Okay, so how do we write it? First, same as before, you write the domain and codomain. And this is the same as before. This is to say that f is a function. For each element x in the domain, there is exactly one element y in the codomain that is mapped. And this is a new rule that you have to write. Okay, so I'm just turning the English description into the language of Klingo. If x is mapped to y and x1 is mapped to y, then x should be equal to x1. That's the definition of one-to-one function. Okay? So let's practice this. When I have 1, 2, 3 and a, b, c, d, e, how many one-to-one functions are there? Do you recall? Don't? Did you forget what we did before? 8? Okay. Okay, we don't have that example here. So let's see how many do we have, okay? And see whether your answer is consistent with what Klingo output. So this is the program that you see, okay? So domain, codomain, and then this is to represent this is a function, and this is to say this is a one-to-one, okay? Klingo. One-to-one. I put 0. There's 60. And you can check whether each of them makes sense. If you look at this, 1 is mapped to one of A, B, C, D, E. 2 is mapped to the remaining of the A, B, C, D, E. And then 3 is mapping to another remaining of A, B, C, D, E. Meaning that 1 has 5 choices, 2 has 4 choices, and 3 has 3 choices. So 5 times 4 times 3 is actually 60. So that's what you get here. Okay? So as you see that each of the stable model here represent the function. So if you count how many functions are there, you just see how many stable models are there. Okay. Any question up to this part? All right. The next one is about onto function. So what is onto function? Onto function means that it's a function, but for every element in the codomain, there should be at least one element from the domain that is associated. So none of the element in the codomain is left out. That's what onto function is about, right? So for instance, here, how many onto functions are there? Well, everything has to be mapped to 1, mapped to A, so there's 1. How many onto functions are here? Then everything here is mapped to either A or B. So it removes the two answers where everything is mapped to A and everything is mapped to B. They are removed, right? So among the eight possible functions, 2 of them are not onto. So the remaining 6 becomes onto function. That's what we have. So let's see how we formulate onto function. So again, this is same as before, and this is also same as before. This is to say that f is a function. But now we want to say onto function. What do we have as definition of onto? Onto is saying that for each element y, there should be at least one element x. Okay? How do we say at least one element in x? Can you guess how to write it? Not no? Yeah, something like that, yes. Hand waving here.
Not codomain.
Aha. Okay. So this is the one, yes, similar to what you just say. So now the codomain here is the global variable. For each element in codomain, x, the mapping x should not be equal to 0, meaning that there should be at least one x that is mapped. Okay? If some element of y has no association to x in the domain, then this violates the constraint, meaning that that's not an onto function. Okay, so let me repeat. It's actually interesting use of the local and global variable. Global variable is kind of fixing one element. So pick one element from the codomain. And if you see that none of the x is mapped to that element, then this violates the constraint. Okay? Now let's actually look at the thing. So this is the function, onto function. So here I say that the same thing as I just did. Actually, I have another line which I commented out for now, but it can be also written this way too. Okay, so actually, maybe let's also talk about this rule. This rule is saying for each element of y, there must the codomain. There should be at least one element in the domain that is mapped to y. It's not equal to 0. So either you can put this one into the right-hand side of the this symbol, or you can put it in the left side, but you have to negate it. Okay, that makes sense. If there's a y, then there should be at least one x. Okay, if there's a y, if none of them x is mapped, then this violates constraint. They have the same meaning. Okay? So let's see how many onto functions are here. Do you recall how many onto functions are here? If you have 1, 2, 3, 4, 5, 6 as domain and ABC as a codomain, it's a bit of complicated functions that we write. Do you recall? $540 was the answer. And remember, actually, 540, it only took 0.008 seconds to return. It's too fast, so you cannot even see all the 540 answers. Okay? You can check. Okay? So each of them is actually onto. Let's actually look at answer 75, for instance. 75 has 6 is mapped to A, B, 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 C. So at least all ABC has at least one element that is mapped from X. Okay, same for all the others. ABC, all the functions use all of the ABC. Okay, that's the definition of 1, 2. All the elements in the codomain have to be used in the function. Any question up to this part? Okay, let's move on then. And maybe this is the last slide for today. It's one-to-one correspondence, which is basically bijective, actually, based. Okay, so one-to-one correspondence is, what is the definition of one-to-one correspondence? It is both one-to-one and onto. Okay, we know how to write onto and one-to-one. So as you can expect, it's actually easy to write. This is a function, okay, and this is saying that this is one-to-one function, and this is onto function. You just write each of the rules together, and that becomes one-to and onto, because that's by the definition. Okay, so you just copy the rules that you have before, and I'm going to skip the running because you'll see that it's actually easy to run through. Okay, all right. So let me stop here. Any question about today's material? Okay, good. Although for the remaining time, I'll ask you the grader to come, and he will explain the solutions to the midterm 2